Hello friends, in this video we are going to discuss what will be the concentration of electrons inside the conduction band of an intrinsic semiconductor, but graphically. We know that according to quantum mechanics, that the density of the states are not uniform inside the conduction band and valence band. So let us understand what does it mean. We know that we have conduction band and valence band inside a semiconductor. So this is the energy band diagram where this will be the EC energy level and this is the EV energy level and this is the band gap of this semiconductor. Now this energy level will be minus infinite energy level and the maximum energy level of the conduction band will be plus infinite energy level. So this is the conduction band and this will be the valence band. Now we know that this total conduction band is covered with a large number of energy states. Similarly, there will be large number of energy states inside this valence band. Now, according to quantum mechanics, it states that the density of these energy states in these bands are not uniform throughout this. That means there is a variation in the density of these energy states inside this conduction band and valence band, and this is denoted by a term called distribution of energy states. So this density of states is nothing but the distribution of energy state and this distribution of the energy state inside the conduction band and the valence band will be determined by a function called distribution function of energy state, and that is nothing but n c e and n v e. So nce is the distribution function of energy states in conduction band. Similarly, nv of E is the distribution function of energy states for valence band. Now let us see what this distribution function means and what does it specify. The distribution function gives that how the energy states in the conduction band and how the energy states in the valence band are distributed over the energy. And we have seen that in the conduction band it is determined by the function Nc of capital E, and in valence band it is determined by NV of capital E. So, we have earlier seen that this distribution function can be plotted with respect to the energy scale. So, let us put the NC E and NV E in an energy diagram. So, if this is the energy axis and if it is the energy state distribution axis, that is NE, then let us define that this is the EV energy and this is the EC energy, and let us define this value is plus infinite and this is minus infinite on this energy scale. According to the quantum mechanics, we know that this space is nothing but the conduction band and this energy space is nothing but the valence band, and this gap between the conduction band and the valence band, we know that it is nothing but the energy band gap. Now, within the conduction band, the energy states are distributed in this fashion that in the middle of the conduction band, the energy state density are very high, like this. There are closely spaced energy states inside the conduction band at the middle of the band. As we move towards the band edges in the conduction band, then the density of the energy states decreases. Similarly, for the upper band edge. So, from this picture or figure, we can see that at the center of the conduction band, the energy states are highly dense, and as we move towards the band edges, the energy states are not so dense. So, we can plot the distribution function, and this distribution function is nothing but given by this NCE, and this NCE can be plotted like this, where you can see that at the middle of the conduction band the value of NC is high. As we are moving towards the band edges, the NCE value is decreasing and NCE value is decreasing. Similarly, we can find that for the conduction band, the energy states are similarly distributed inside the valence band. Likewise, at the middle of the band gap, we are getting a very high value of NVE, and as we are moving towards the band edges, the NVE value is decreasing and NVE value is decreasing. So, let us plot this NV and NCE value in the figure 2 in this fashion. So this is the plot for NCE, and this is the plot for NVE. So we can write it as NCE, that is the distribution function of energy state inside the conduction band, and this is the distribution function of energy state inside the valence band, that is NVE. So from this graph we can see at the middle of the conduction band NC value is highest and NV value is highest at the middle of the valence band. Now let us take a elemental energy in the conduction band and as well as in the valence band. So the elemental energy is like this. So this part is an elemental energy where or infinitely small amount of energy, that is dE. Similarly, we can take a very small amount of energy gap in the valence band, which is nothing but dE. So this area, this small ribbon area, will give total number of energy state inside the d amount of energy. So we can write this shaded region will give shaded region will give total number of energy states within the energy difference dE in the conduction band. Similarly, this statement can be written in an equation form as Nc into of E into dE. So if I want to find the total number of energy state inside the conduction band, then we have to do a integration over EC2 plus infinite. So the total number of energy states in the conduction band will be integration EC2 plus infinite NCE into dE. Similarly, for the conduction band, this shaded region will give that NV into E into dE. So the total number of energy state in the valence band will be, the integration limit will be from minus infinite to plus EV, and it will be NV E into dE. So we have found the total number of energy states inside the conduction band and valence band. Now we need to find the concentration of electrons inside the valence band and concentration of electrons inside the conduction band. So for that we need to know what is the distribution of electrons inside the energy states of the conduction band and valence band. So the distribution function for electrons will be needed, and this distribution function of electrons within the conduction band is given by the Fermi-Dirac function. That is f of Et, and we know that according to the Fermi-Dirac statistics, the FET vary with the energy as well as temperature. So let us plot the FET with respect to energy, and let us define that this is the Fermi level of the semiconductor and this is zero energy. So this is the one value of the FET, and we know that the FET will look like this one. The value of the FET or graph will look like this one. So this is the nature of the FET inside the semiconductor. Now if I superimpose this FET on the previous graph, then I can find the value of concentration in the conduction band. So let us superimpose this FET graph on the NCE graph, and it will look like this. If this is the energy axis, and if this is the value of NE, we know that this is EV and this will be EC. So we can say that this gap is the EG. Now we know that the nature of the NCE looks like this, where this energy is plus infinite, and the nature of NVE will look like this one, where the value of this energy is minus infinite. Now we have already taken the FET, so let us put the FET in this graph. So the FET graph will look like this one. Hence, the common area is this dotted region of these two graph. So this dotted region is the common area between these two graph, where this graph is for FET and this black graph is for NCE. Now, if I take an elemental area on this common region, then it will be look like this. So this is the elemental area that has a energy value of dE, and this elemental area will give the number of electrons per unit volume for dE differential energy. That means it is equals to NCE into FET into dE. So the total concentration can be found by taking the integration. Total concentration will be integration EC to plus infinite NCE into FET into dE. So this will give the total concentration of electron inside the conduction band. Similarly, we can find the total concentration of holes in the valence band. For that, we have to take the distribution function of holes in the valence band, and we know it is nothing but 1 minus Fe. So the total concentration of holes in the valence band can be written as integration, and the integration limit will be minus infinite to EV into NVE into 1 minus Fe dE. So in this way we can calculate the concentration of electrons and holes inside the semiconductor by a graphical approach. So this is all about this topic. Thank you.